Hello everyone, this module will be discussing the applications of integration. In this particular unit, one application to be discussed will be solving plane areas in Cartesian coordinates. To solve plane areas in Cartesian coordinates, we can use the vertical element. Considering the y and the x-axis and a curve whose equation is y is equal to the function of x. If we wanted to solve the area bounded by this curve and the axis, we can introduce the vertical element. The vertical element is a rectangle whose width is a differential of x or dx and whose length is y. Solving the area of this rectangle is a differential area equivalent to y dx. Y is the length and dx is the width. If we integrate both sides of the equation, area or A will be equivalent to the integral of y dx. Let us consider this point. This point will be having coordinates equivalent to AB. A is the x coordinate and B is the y coordinate. A becomes the lower limit. So the lower limit A is the lower limit of our integral. If we consider a second point, whose coordinates will be A prime, B prime. A prime is the x coordinate and B prime is the y coordinate. A prime becomes the upper limit. So this upper limit, A prime, is the upper limit of our integral. We know that y is equal to the function of x. We have to express y in terms of x because x is our variable of integration. So substituting y is equal to the function of x will be giving us the formula to solve this particular area. The area is the integral from a to a prime of the function of x dx. Let us solve for the first quadrant area bounded by the parabola y squared is equal to 4ax, the x-axis and the line x is equal to a. The parabola y squared is equal to 4ax is a parabola that opens to the right with a vertex at the origin. The line x is equal to a is a vertical line. We wanted to solve the area bounded by this parabola, the line x is equal to a, and the x-axis. We can use a vertical element whose width is dx and whose length is y. The origin is the vertex of the parabola at 0, 0. Another point is at a 0 and another point of intersection is at a and 2a. To solve the differential area, this is equivalent to y dx. Y is the length and dx is the width of the element. Integrating both sides, we get the area or A is equal to the integral of y dx. The lower limit is 0 and the upper limit is a. From y squared is equal to 4ax, we can solve y as a function of x, where y is equal to 2a raised to 1 half x raised to 1 half. We substitute this value of y into the integral. So we get a is equal to the integral from 0 to a of 2a raised to 1 half x raised to 1 half dx. Integrating, we get a is equal to 2a raised to 1 half times x raised to 3 halves all over 3 halves with limits from 0 to a. Evaluating this definite integral, we get an answer of 4 all over 3 a squared square units. To solve plane areas in Cartesian coordinates, we can use the horizontal element. Considering the y-axis and the x-axis and a curve whose equation is equivalent to y as a function of x, or x is equal to the function of y. If we wanted to solve the area bounded by this curve and the axis, we can introduce a horizontal element. A horizontal element whose width is equal to the differential of y, or dy, and whose length is equal to x. Solving the area of this rectangle is a differential area equivalent to x dy. X is the length and dy is the width. If we integrate both sides of the equation, it will give us the area, or A is equal to the integral of x dy. Considering this point, whose coordinates will be equal to A prime, B prime. B prime is the lower limit. This lower limit is the lower limit of our integral. If we consider another point, whose coordinates will be equal to AB. B is the upper limit, and this upper limit is the upper limit of our integral, which is B. We have to express x as a function of y because y is the variable of integration. Substituting x is equal to the function of y will give us the formula to solve this particular area, equivalent to the integral from b prime to b of the function of y dy. Let us solve the first quadrant area, bounded by the parabola y squared is equal to 4ax, the x-axis, and the line x is equal to a. The parabola y squared is equal to 4ax opens to the right with a vertex at the origin. The line x is equal to a is a vertical line. We wanted to solve for the area bounded by the parabola, the line, and the x-axis. We can use the horizontal element, whose width is equal to the differential of y, or dy. XL is the x on the left part of the element, which happen to be the parabola, which is equal to y squared is equal to 4ax. XR is the x on the right part of the element, and it happened to be the line x is equal to a. To solve the differential area, it is equal to the difference of XR and XL multiplied by dy. Integrating both sides, we get the area, or A, is equal to the integral of the quantity XR minus XL dy. If we consider the point of intersection of the x-axis and the line x is equal to a, the coordinates will be a, 0. 0 is the lower limit of the integral. The other point of intersection is the intersection of the line x is equal to a and the parabola y squared is equal to 4ax. And the coordinates will be a and 2a. 2a is the y coordinate, and it is the upper limit of the integral, which is 2a. XR is the line x is equal to a, and XL is the parabola equal to y squared over 4a. Substituting, we get the area equivalent to the integral from 0 to a of the quantity a minus y squared over 4a times dy. Integrating, we get the area to be equal to AY minus Y cubed over 12A with limits from 0 to 2A. Evaluating further, we get a final answer of 4 over 3 A squared square units.